Assalamu alaikum. Anyway, it's not very perfect, but for starters, I think you can read. So let's just start. Um, anyway, so this is just I wanted to introduce you to. We already spoke about this, so this is a follow up. So these are the videos I'll be making and upload by, let's say, Wednesday or Thursday. So this is just for this week what we have done, an overview of everything, and then you will find it in the mood, of course. Okay. So straight away we had we were just introducing. We are reviewing section 1.1, 1.3, and 1.4. And anyway, so what we were talking about, one is a proposition or a statement. We just said it's a declarative sentence that is either true or false, but not both. In other words, it tells you something which you can verify whether it's true or false. Finish. Then the truth value, a proposition, once you are verified is true, then you denote it by true. If it's false, you denote it by false. And whatever, that what you're verifying is called a truth value of any given proposition or statement. Okay? Then propositions that cannot be expressed in terms of simpler propositions are called atomic propositions as opposed to compound propositions. Basically, when a proposition just gives you one, fact to verify. That's what we were saying, like it is called, just that. You cannot break it into simpler. And we use PQRS to represent them, just like in calculus, in functions, we used to use X for variables, okay? Then the branch that deals with this logic is called propositional logic or calculus. And we use what we call logical operators or connectives to join simple statements or propositions or atomic propositions to compound propositions. So straight away we go next to the what you call the logical operators. And the logical operators, the first one we're talking about is negation. The negation of a given proposition P, denoted by this P, is a statement. It is not the case P. It is cold, it is not cold. It is raining, it is not raining. Next, conjunction. What we call a conjunction or AND of two propositions P and Q, denoted by P and Q, is a proposition P and Q. And this is true when both are true and false otherwise. Okay? So this is important to keep in mind for the future laws that we saw. Then the distinction of P and Q, denoted by P or Q, is a proposition P or Q. It is false when both P and Q are false. Otherwise, it's always true. Then the conditional, one-way conditional. This is basically P implies Q. So P is a condition for Q, or you call this a premise, and this conclusion. Okay? And this is always true except when P is true and Q false. Finish. Then the biconditional statement that P implies Q and Q implies P. So this is in mathematics we read it as P even only if Q. And it's true when both have the same truth values. Otherwise it's false. Finish? Yes, finish. This is just an overview, so you already saw this this week. Then, definition. The converse of the proposition P implies Q is Q implies P. You just go the other direction. The contrapositive of the proposition P implies Q is negation of Q implies negation of P. This is very important. You will see it from time to time. And then the inverse of the proposition P implies Q is negation of P implies negation of Q. Finish. Okay. Then propositions with the same truth values are said to be logically equivalent, and we use this symbol. We never say propositions are equal. Never. Example, the contraposition P plus Q is equivalent to its contrapositive. These are equivalent. You can verify this. The conjunction and conditional, that P plus Q is equivalent to negation of P or Q. And then De Morgan's laws, actually here I can just say, because later on you saw the example, I'm just repeating and doing a recap. So the negation of P or Q is the negation of P and negation of Q. If here we had P and Q, then we would have negation of P or negation of Q would be the value. Finish. Next is tautology, contradiction, contingency. I just say Tautology is where the statement makes sense. It's true, it's valid. All true values are true. If everything it doesn't make sense, it's a contradiction. It is raining, it is not raining. Doesn't make sense. And if you are in doubt, it's either it's true or false, but not, a tautology or contradiction. There's a contingency. Then the next one I can just skip because you already know. I already told you this. Now, what is it I already told you? Yeah, the laws here, you have them in this book. Since you're going to get the book next week, inshallah, then if you check this table, I just copied for you here. So here is a table. This we went through in class. I don't know whether you want me to overview again, since I'm just doing an overview. So what do the law says? The identity law just says that, identity like 0 plus 1. 0 is identity. 0 plus 1 gives you 1. So this is what we're doing. So you take P and true, it gives you P. P or false gives you P. So you can see P is the identity here. Okay, it's behaving like the identity. Then domination. Now in this case it will dominate. So P, what dominates is false and the true. They sort of exchange, the property here. So P and F is false. False is stronger. P or true is true. Okay? Then idempotent law or property, you can think of it like 1 plus 1 squared is 1. So 1 is idempotent with respect to multiplication. That's for numbers. Now here in logic, what you have is P, and P is equivalent to P, and obviously P or P is P. Then you have double negation. The negation of P is P. I don't need to say anything. Commutative just says that when you are operating on 2, then the order doesn't matter in terms of logic. P and Q is the same as Q and P. P or Q is equivalent to Q or P. Okay? Then associative is more or less this one, but now 3 of them. If you have 3 of them with the same property, then you have P and Q and R the same as P and Q and R. The next one is the same. P or Q or R should be P. This should be OR, by the way, it's a mistake. So P or Q or R. Finish. Then distributive property just says that you change these two. So you have, either this or that. And how you do distribute? Well, I should show you. The distribution is just like you fix this, and then you will have P or R, which is that one. And then you have Q or R, which is this one. And then you join with that disjunction that you blocked. So you have distributed R inside here. Then you can also distribute it inside here. You have P and R, Q and R, then you join with R of the disjunction OR. Okay? Then absorption, this is just absorbing. P or P and Q is equivalent to P. This actually is nice for you to verify. It's not too hard to do that. P and P or Q is P. And finally, you have negation. Negation. Negation just says that when you take disjunction of a statement with this negative, then that's a tautology. Either you are here or you are not here. Only one is true. So it's true, eh? Then P and P and negation of P is a contradiction. Finish? Finish. Okay, then now the last part which you did was about the predicates, quantifiers, and this. So one thing I should say is that this is called a propositional function, where you have a statement or a proposition, but it has what you call subjects, okay? That sort of you have to verify for each of them, okay? And so the property you give to the variables, you call it predicate, and these are the subjects, okay? The case at hand I gave you was, all of you are good students. So I have to check each one of you. So each one of you is a variable, and the predicate is that fact that you are good, okay? And then we said that there are 4 of them. One is what you call universal, that this statement is true for all x. We denote it by this. Then we talk of a counterexample, something that doesn't satisfy the property. We would call it a counterexample of the subjects of variables. Then existential quantifier, that there exists some values for which this statement is true. And then uniqueness is there exists a specific value for which this statement is true. Then we call it unique quantifier. Okay? Fine. Then I gave you this example, which we talked about. We say that the day is cloudy. Okay, so here it's like the question here is, we determine which of the following are statements and identify the connectors or the logic operator. So 1, the day is cloudy. It's just a simple statement, so there's no connector, nothing. Next, it is a clear night and the moon is shining brightly. Well, you can see this is a conjunction. It's a statement joined with a conjunction, P and Q. Determine which set contains the other set. That is not a statement, forget it. It is neither your problem nor mine to know who comes late to class. Well, this one I should say that, well, I told you this, you can see this negation. So this is like negation of P. P would be, it is your problem. So it is neither your problem, is now negation of P, joined with a disjunction or negation of Q, which is now, it is my problem, now it's not my problem. And then second last or third last, airline flights from New York to New Delhi are delayed this morning. Well, this is only saying one thing, so it's a simple statement, okay? If a person speaks English, then he or she speaks Chinese. So basically, now this is actually a tricky one because of this he or she. But this is not in terms of the connective. This is just like specifying so that people don't say you're discriminating. So this is just if, then. So just P implies Q. Finish. The last one, creatures fly if and only if they are birds. Well, we know that there are other creatures that don't fly. So this is a biconditional. I don't need to say many more things. Well, I'm sort of looking at the watch so I make sure the video is not too long. So I'll have to make maybe 2 of them. Then this one I told you the sample quiz. So, I mean, you just need to remember, again, identifying these kind of things, that this is if P and Q. So P and Q implies R. Then this would be negation of this one, and this is negation of this one, and this is still the same R. Finish. This I don't need to say anything, I just need you to see these two are equivalent as statements. That I already repeated. And then lastly, where you can verify that they are, well, this will be a simple statement. It's like a theorem to be proven. Anyway, that we'll see later on. Okay? Let's see what else we can do before. So actually it's not bad. Maybe we may be able to finish this before we run out of time. Let's see whether we can do it in 3 minutes. So, show that this is a tautology without using truth tables. So, we do it in 2 ways. One, we'll assume, no, anyway, let me start this in the next video. It will be maybe 5 minutes. Okay, so let me take a break there.